On problem 4, I want to stress that there are a lot of different possible solutions to this question. All you've been asked to do is create different trig expressions that would simplify down to sine of x that involve multiple trig functions, one that involves a Pythagorean identity and one that involves division. This is challenging. You sort of have to almost work your simplification process backwards. I have several different possibilities listed within the answer key. I'm going to walk through how you might approach a few of them. And, from there, you can sort of try to come up with some on your own. The best way to test if your answers are correct would be to graph your expression you wrote and graph sine of x and see if the two graphs match up. For this first problem, I'm going to look at creating one that involves division and obviously multiple trig expressions. So for my thought process, I start with where I want to end up. I want to end up with sine of x. So I have sine of x. Okay, well, sine of x is equal to 1 over cosecant x. I got a division in there. And cosecant of x is the reciprocal of sine of x. So I could even take this a step further and say this fraction is really equal to 1 over sine of x. So this is where I want to end up. And I need to think about how could I get that 1 over sine of x in the denominator of a fraction, because I know that would simplify to cosecant x, which would simplify down to sine. So let's start with the 1 in the numerator. And in the denominator, what if I tried a 1 over cosine of x? That's not what I'm looking for, but it's a place to start. And if I multiplied that by cosine of x, that would simplify to 1. But I want 1 over sine of x, so what if I divide that by sine of x? So now if I look at these two problems, I have cosine of x over sine of x times 1 over cosine of x. Those two cosines of x would simplify down to 1. And so I'd be left with 1 over sine of x in the denominator, which is what I pointed out above that I was looking for. Okay, so far so good. Let's just sort of rewrite this into single trig expressions. So cosine of x over sine of x is really cotangent of x, and 1 over cosine of x is secant of x. I have my quotient problem with multiple trig expressions, which is exactly what we were asked to do. And I know it simplifies back down to sine because I sort of worked my way backwards. Now that we've done the quotient problem, let's try and tackle the one that involves a Pythagorean identity. So remember, 1 minus cosine squared x equals sine squared x. And that's a good thing to keep in mind with this particular one, because if I did 1 minus cosine squared x, what would I need to divide by to get back to sine of x? Well, just sine of x. And ta-da, I'm done. That's my problem. It comes out to sine of x. It's as simple as that. It would be sine squared of x over sine of x, which simplifies to sine of x. Now, I could rewrite this a little bit to get a third expression, because this is really the same thing as 1 minus cosine squared x times 1 over sine of x. And 1 over sine of x is the same thing as, delete that, cosecant of x. So I could say 1 minus cosine squared x times cosecant x. And I could distribute that cosecant x. So I have cosecant x minus cosine squared x times cosecant x. And this also would simplify down to sine. And you'll sort of just notice my simplification problem is just working backwards. I sort of started where I wanted to end up, and I sort of kept making it more and more complicated as I worked my way down the page. I stress again, if to see some additional examples, go click on the solutions and you'll see some of the other versions of these expressions you could come up with, and check your own by graphing them. Let's move on to solving some equations with identities. So we're being asked to solve our trig equations on the intervals 0 to 2 pi, but we got to simplify first with the identities that are on our sheet so that we can sort of get down to a single trig expression and then use some inverse trig. So on this first one, we have tangent of negative x times cosecant of x equals 1.4. Well, tangent of negative x is really just negative tangent of x times cosecant of x, and it's, equal to 1.4. We can then, rewrite in terms of sine and cosine. So tangent of x is sine of x over cosine of x. Cosecant is 1 over sine of x. That still equals 1.4. Let's fill that in. And then I can reduce a little. So sine over sine cancels to 1. And so I have negative 1 over cosine of x equals 1.4. Now I could treat these both like fractions. That would be 1.4 over 1. And since I have two fractions here, I could take the reciprocal of both and they will still be equivalent. So I can really think of this as negative cosine of x equals 1 over 1.4. Multiply both sides by negative 1. So cosine of x equals negative 1 over 1.4. The next step would then be to move on to using our inverse trig. So inverse cosine of that negative 1 over 1.4 would get us our first possible solution of 2.366. And yes, we should be working in radians. That angle would be in quadrant 2. So its matching value cosine would be in quadrant 3. I can find that by doing 2 pi minus that value, and I wind up with 3.917 as my second solution. Our next problem is going to involve using a Pythagorean identity here before we simplify in terms of sine and cosine. So 1 minus sine squared x is equal to cosine squared x. That's times secant, which is 1 over cosine of x. And that's still equal to negative 0.1. Cosine squared times 1 over cosine of x would just be cosine of x equals negative 0.1. Using inverse cosine of negative 0.1 to find our angle measure, which would come out at 1.671. That would be an angle in quadrant 2. Its matching angle would be in quadrant 3. 2 pi minus 1.671 would get me that matching angle, and that would be at 4.612. All right, moving on to the next set of problems. These get a little more complicated with some squareds going on in here. So in this first one, I chose to replace that double angle. I don't like having it in there if I don't need it. And so I'm going to use the version that has a cosine squared in it because that's what's on the other side. So in this particular case, it would end up becoming a 2 cosine squared x minus 1. I can now combine my cosine squared x's and move them both to the same side of the equation and the 1 to the other side. So I would end up with 1 equals 4 cosine squared x. I need to divide out that 4, so 1/4 equals cosine squared x. Now when we're dealing with a squared here, we're actually going to wind up with 4 solutions to our problem because we could square a positive or negative version of a number and get the same answer. So I like to sort of split this into 2 separate equations at this point. One, cosine of x equals positive 1/2, and the other would be cosine of x equals negative 1/2, and that's the square root of 1/4. And now I'm going to do the inverse of both of these. So I would take the inverse cosine of 1/2, and that comes out to, and then the inverse cosine of negative 1/2. And so each of these are going to get me 2 of my solutions. And from there, I then need to get the third and fourth solution. So the inverse cosine of 1/2 is actually an even number. It's 60 degrees or pi over 3. And the inverse cosine of negative 1/2 would be 2 pi over 3. It's in quadrant 2. And so their matching angles would in quadrant 1 would fall in quadrant 4. And so that would actually end up being 5 pi over 3. And then the matching angle for our one in quadrant 2 would be in quadrant 3, and that would be 4 pi over 3. And you could plug these into the calculator to see the decimal form of these numbers. I just sort of keep them in the pi over 3 setup, and that's fine and a perfectly acceptable. On this next equation, you could rewrite this in terms of cosecant squared x or cotangent squared x. I chose to replace on the left side because there's only a single term there, and cosecant squared x is equal to cotangent squared x plus 1, and that equals 3 minus 2 cotangent squared x. And so now I can sort of group my cotangents on the same side and my non-cotangent terms on the same side to make my equation a little simpler to solve. So cotangent squared x, and then I would add 2 cotangent squared x to that, which would be 3 cotangent squared x. And then that equals 3 minus 1, which is 2. Divide both sides by 3 gets me cotangent squared x equals 2/3. Now here's where I'm going to end up with my 2 separate equations again, because I'm going to have to undo the square by taking the square root. So I like to think of this as cotangent x equals the positive square root of 2/3, but it could also come out to be the negative square root of 2/3. And I need to take the inverse of both of these. Now, inverse cotangent I can do using Desmos, so I don't need to worry about finding reciprocals here, and I'm just not going to. And so I would go through and I would take inverse cotangent, pardon my language, of square root of 2/3. And from that, I would come up with the value of 0.886. And that's my first solution. And that would be in quadrant 1. And if we're sort of keeping in mind it's cotangent like tangent, the matching angle would actually fall in quadrant 3. And I could find that by adding just pi to the answer I came up with, which would be 4.028. I'm going to repeat this process for the other cotangent of x expression I have. So I have cotangent of x, so I'm going to do inverse cotangent of negative square root 2/3. And that's going to come up with the measure of 2.256, which is in quadrant 2. Its pair would be in quadrant 4. I can find it by adding pi to this angle measure, and I would come up with 5.397. Moving on to our final 2 equations. On this next one, it really doesn't matter if you tackle the tangent squared x or the secant squared x. It's your pick. I'm going to replace the tangent squared x just because that side looks a little simpler to deal with. So tangent squared x is equal to secant squared x minus 1. And you might be wondering where that comes from, but that's a Pythagorean identity. We know that tangent squared x plus 1 equals secant squared x. And so if you minus the 1 to the other side, you would end up with tangent squared x equals secant squared x minus 1. It's a helpful version. That's, in this case, in this equation, it's equal to 0.33 secant squared x. We get my secants on the same side of the equation and my secants on the other. So I have negative 1 equals 0.67, that make that a negative 0.67 secant squared x. Divide both sides by 0.67, so I get 1 over 0.67 secant squared x. Now I am able to take the reciprocal of something like that even though there's a squared going on. That's not really going to impact it. So I could think of this instead as just 0.67 equals, instead of secant, the reciprocal of that would be cosine squared x. Just makes it a little easier to deal with inverses here. I'm going to take the square root though first before I deal with my inverse to get my two separate equations because I'm going to have multiple solutions. So cosine of x equals the square root of 0.67, but it could also equal the square root of negative 0.67 or negative square root of 0.67. Now I'm ready to take some inverse functions now that I have my two equations. So looking at, I'm going to do the inverse cosine of the square root of 0.67. That's going to get me my very first solution of 0.612, which falls in quadrant 1. Cosine is a horizontal distance, so its matching angle will be in quadrant 4. So 2 pi minus that 0.612 is going to get me my second angle of 5.671. So I have 2 of my 4 solutions so far. Now I'm going to do the same thing with the negative possibility. So I'm going to do inverse cosine of negative square root of 0.67. And that's going to come out at 2.530. That would be an angle measure in quadrant 2, as we can sort of see in this little drawing. And so to get the matching angle, we would go to quadrant 3. 2 pi minus that value would get me there, and it should come out at 3.754. Our final equation actually ends up being a lot simpler than the previous ones. So first step, we're going to sort of simplify that cotangent of pi over 2 minus x. That really just simplifies to tangent of x. Okay, that's easy. Equals 5 plus, and that tangent of negative x is really negative tangent of x, so negative 2 tangent of x. Let's get our tangents on the same side. So we have 3 tangent of x equals 5. Divide out that 3, tangent of x equals 5/3. You're looking, oh my goodness, just got a slope. Let's use some inverse tangent. I don't need multiple equations set up. So inverse tangent of 5/3, which would come out at 1.03. Once you put that in your calculator. And that would be a solution in quadrant 1. Tangent's a slope, so it's matching angles in quadrant 3. I can find it by simply just adding pi 1 period further along in the function. That's 4.172. And that's all there really is to this. And hopefully now you have a better sense of how we might use trig identities in different types of problems.